The median age of residents of the United States is 37.2 years. If a survey of 200 residents is taken, approximate the probability that at least 110 will be under 37.2 years of age. So there are two random variables involved in this problem. The first random variable will talk about the age of a single resident. So we must find the probability of a single resident's age being less than 37.2. Okay, so we name x as the age of a resident random variable. Now this is actually given to you because it says the median age of residents of the United States is 37.2. So the median means half of the people in the United States will be older than 37.2 years of age, and half of the people in the United States, half of the residents, will be younger than 37.2 years of age, right? So the probability of being younger than 37.2 is going to be 1/2, because the median divides the total area in half, okay, at the value of 37.2, okay? So that's good. So now we found the individual probability of someone being younger than 37.2 years of age, 1/2, okay? So now we're going to let the second random variable represent the number of people under 37.2 years of age. And notice I'm saying the number of people. I'm not just talking about a single person now. I'm talking about multiple people, more than one person, right? This is another random variable. So how do we go from there? So notice that we're being asked in this problem is to find the probability that at least 110 will be under 37.2 years of age out of 200, right? So we need to find the probability of y being greater than or equal to, because it says at least 110, okay? Because we already specified that the y random variable was the number of people under 37.2 years of age, so we're trying to find the probability of this random variable exceeding or being at least equal to 110 people. So to do that, notice that you need to, in order to use the z-table, you need to write it as 1 minus the probability of the random variable y being less than or equal to 109. Okay? Because you don't want to count those people. You don't want to count the numbers of people being 109 and less and fewer, right? You want to count 110 and above. So you want to subtract from 1 the total probability. You want to subtract from that all the possible combinations of 109 or 108 or 107 or 106 all the way until you get to 0, right? The number of people under 37.2 years of age. So now that we have that, notice that here we can be successful because we can, instead of using the binomial, this calls for the binomial distribution. Instead of using the binomial, because this is 109 different terms that we will have to use the binomial distribution for, so that's going to be too much, right? You don't have all day to to do that. So instead, we want to approximate this probability using normal distribution. And why is this going to work? It's going to work because central limit theorem guarantees that as long as your sample is at least 30 and above, you can approximate the binomial distribution using normal, right? Normal distribution. And this is definitely way more than, 30, right? Because you're talking about 109 terms. Okay? And yeah, and so let's see how this is done. So you're going to use continuity correction because you're talking about binomial, right? And you will use continuity correction to account for the differences between, the curve and also the rectangles that you use for your discrete. I will explain. So this is suppose this is normal, in a normal curve, as you can see, you can use, let's say, points and rectangles that are accounted for by the binomial distribution, because this is a discrete distribution, right? So you would use rectangles or histograms for that. However, for normal distribution, it's a continuous distribution, right? So you don't need the rectangles. But notice that some parts that are inside the curve are outside the rectangles, okay? Like these parts. However, there are parts that are outside the curve but inside the rectangles, all right? This would be this part here, okay? Like this part here. That's outside the curve but inside the rectangles. So to account for this discrepancy, right, because this looks like it's going to be not, it's going to undercount or overcount certain things, you want to use continuity correction, right? And the continuity correction basically tells you that when you have the upper boundary, in this case 109 is the upper boundary, right? That's the maximum value. You have to add 1/2 to it. So it's going to be 109 plus 1/2. So we're talking about 1 minus the probability of, and by the way, you should correct this. Also make sure that this is erased and it's going to be less than only. And the reason why it's less than is because you added 1/2. So 109 was the maximum. If you add 1/2, you're not going to be equaling that. It's going to be less than that now, right? So as a result, this is equal to 109.5. Now we're going to use the z distribution, okay? And you can write this as 1 minus the probability of z less than or equal to 109 minus the mu, the mean, divided by the standard deviation, okay? So now recall the reason why we converted y into z is because we can express z, as y minus mu divided by this, the standard deviation sigma, right? So recall that, and whenever so if I subtract mu and then divide that by the sigma, I have to do the same thing to the right side of the inequality, which I did here. So the left side becomes a z, and the right side becomes 109, and I should have corrected that. This should be 109.5. So I'm going to make that correction very quickly. 109.5 minus the mu divided by sigma. Okay, now you might say, but how do you know the mu and sigma? Well, the mu is pretty easy to find. The mu is going to be NP. The n is going to be the number of people, in this case 200. Recall that in the binomial distribution, the mean is going to be the n, the number, in this case 200, times the probability. And the probability we found was 1/2. And why is this useful? Because these are the parameters that we use. If we were not to use the normal, we would still need these parameters, n and p, right, to use the binomial. But as we said, 109 terms is a lot, right? It's just too much. So we want to use the normal approximation with continuity correction. And for that, we need the mu, which is going to be the same as the binomial, 200 NP, right? 200 times 1/2, that's going to be 100. And now standard deviation, sigma, is going to be n, p, and q. And q is 1 minus the p. Okay, so n, p, q. And square root that, of course. So as a result, this will be equal to NP, we already know, that's 100. That's the mu. Times Q. Q is 1 minus P. 1 minus the probability is 1/2 still, right? So that's good. So this is going to be square root of 50. Okay. So now that we see that, we can write this out here. We can have a proper substitution. So z is going to be less than 109.5 minus 100 divided by square root of 50. Okay, so that's going to be 1 minus the probability of z being less than, and this thing is equal to 1.34, and I'm rounding to 2 decimal places because we're going to use a z-table, and z-table has values for z rounded to two decimal places, right? So I'm not using the complete calculator answer, I'm rounding it to this. So now it's going to be 1 minus, now we need to find the probability of z being less than 1.34. So we need to find the probability, the cumulative probability, for all the z values less than 1.34, right? And to do that, we just look up 1.34 in the z-table, and that will give us the probability value. So 1.34, let's find that here. So we need to find the z of 1 first, and that's going to be right here. So we need 3 and 4 after the decimal here, right? 1.34. So that means we will go, well, actually we need 1.3, right? Because we didn't get there yet. Here's 1.3. And we need 1.34, right? So we need to go to the right to find the 100th decimal place, right? Because we already found the 1, we found the 10th, right? But we need the 100th because we need 1.34, right? So we have to add that to 1.3. So that means we have to go, this is 1.30, 1.31, 1.32, right? Notice it here, 1.32, 1.33, and finally, bingo, 1.34. So I'm going to circle that. This is 1.34, the probability, the cumulative probability for all the z values to the left of 1.34, right? So the probability is 0.9099. So let's go back now and put that down. 0.9099. So as a result, this is equal to 0.0901. Okay? So this is the probability that at least 110 people out of the 200 residents will be under the 37.2 years of age, given that the median age is 37.2. So I hope this was helpful. Thank you so much for watching. See you in the next video.